Hey, Bill here. In our last video, we covered transistors, how they work, how they can be used as switches. We also described how to make basic logic circuits with them. In this video, we'll talk about how you can use all this stuff to do basic mathematical operations. Now, the word computer was once a name given to a job. Back before World War II, computers were people who worked rows and rows of adding machines, computing tables used in applications ranging from ballistics to surveying. Today, if we're going to build a computer, obviously one thing we'd like it to do is to do basic math operations such as addition and subtraction. So let's talk math for a moment. I promise all this elementary school stuff will go somewhere in a minute. When we talk about numbers, we generally are talking about base 10 numbers. That is, we have the digits 0 through 9, and for larger numbers, we add a new digit to the left. This allows us to represent really big numbers, as each new digit to the left is 10 times bigger than the last. Well, the diagram sort of seems redundant because we're talking about base 10 numbers in base 10. But hang on to the idea because it will become useful in a second.
Now, not all cultures use base 10 counting. For example, the Selena Indian tribe of California would count by grasping things between their fingers rather than counting their fingers. Thus, 1, 2, 3, one hand or 4, 5, 6, 7, and two hands or 10. There is a funny story about how researchers asked a Selenan Indian how many fingers and toes he had. He had attempted to count his fingers by grabbing each finger in the other hand, then by grabbing his toes, and finally he answered 2 sets of 2 hands and 3. A set of 2 hands is 8, 2 sets is 16, and 3 more is 19. Apparently he got confused and skipped a finger or a toe.
In base 8 counting used by the Selenan Indians, each new digit to the left is 8 times bigger than the last, rather than 10 times bigger. So the number 156 in base 8 is equal to 110 in base 10. Now, computers don't have fingers and toes. All we have to work with is on and off, 1 and 0. But that's enough if you think about it. Off and on, 0 and 1, gives us 2 digits. This allows us to use base 2 counting with the digits 0 and 1. Of course, we need more digits to represent larger numbers, and that means more transistors. But that's okay. Nowadays, transistors are cheap. Okay, so we now know how to count in base 2. Let's talk addition. When we learned how to do addition in elementary school, we learned to start adding our digits together from the right to the left. We also learned that if our sum was greater than 10, we needed to carry to the next digit. And we then add the next column of digits, carrying if needed, until we had added up all the digits. And voila, we're done. This works in base 2 as well. Remember, we only have the digits 0 and 1, but the process is exactly the same. Now, when we add two base 2 numbers together, we only have 4 possible combinations. And of course, we can rearrange this into a simple table. This is the cool part, by the way, because this is where we start turning all the math we talked about into transistors that can do the math for us. Notice something interesting about our table. The carry column is exactly the same as the AND gate table. This suggests that we can use an AND gate in order to build our carry. The sum column, well, that takes a little more effort. Notice the sum is 1 unless both inputs are 0 or both inputs are 1. We'll just have to be a little more clever to get this result. There are several ways we can do this, but here's one. Suppose we had an OR gate, which is 1 if A or B are 1, and we add the results of a NAND gate, which is 1 unless A and B are both 1. Now notice that our sum column is 1 if both our OR column and our NAND column are 1. This means we get the desired result by adding an AND gate to our previous 2 gates. And this gives us an idea how to build our addition circuit. Our carry result is produced by this AND gate. and our sum result is produced by this collection of 3 gates we put together earlier. Before we go any further, let's note something. These 3 gates, which turn on only if one of the inputs is turned on, is such a common operation we have a separate logic gate we use for them. We use this symbol to mean exclusive OR, and it turns on only if one of the 2 inputs, but not both, are turned on. This is an example of the idea of encapsulation we were talking about before. Instead of tracking the 3 gates that make up our exclusive OR circuit, we simply use this symbol instead. We're keeping things simple for ourselves. Okay, so let's clean this up. This collection of gates then does addition. Notice this matches our earlier truth table. As we add these 2 base 2 numbers, we get a base 2 result. We call this a half adder circuit because, well, it only does half the job we need it to. We'll need to do more work if we want to handle carry from the column on our right. Regardless, let's simplify things for us by encapsulating it in another box. We've sort of run out of symbols, so we'll just label what our box does. So far we've added A and B, but in order to handle our full addition problem, we need to also add in our carry. One way to do this is by adding another half adder to add in our carry to the sum of our 2 previous digits. And that sort of works. We can add the carry to the sum of the previous half adder, but what about the carry output? Well, the output of our first adder is the sum of the first 2 digits A and B. The result is either 0, 1, or 2. So what happens if we add the carry bit into the results in our second adder? Well, what happens is this. The second adder outputs the sum of S and C in. That is, we get a number from 0 to 2, which represents the sum of the last adder and the carry in digit. What we want, however, is the sum of both A, B, and C, which in base 2 looks like this. Notice something about the carry digits? Yeah, the carry in our final sum is 1 if either the first carry from our first adder or the second carry from our second adder is 1, which makes sense if you think about it. Since the largest value we can get from adding 3 ones together is 3, if either adder sums to a value greater than 2, we need to carry. Also notice, that looks like an OR circuit. So let's add an OR circuit. Now that we have our circuit, let's run through all the possible combinations. This is our full adder circuit. It can add up to 3 base 2 digits together and give us a result. And as we did before, let's encapsulate it into its own box in order to keep things simple for ourselves. Now you may think, whoop-de-doo, we can count to 3, but notice what happens when we chain these adders together. We can now add bigger numbers. For example, let's add 5 to 7. In base 2, 5 and 7 look like this. Now remember our convention, 1 is on and 0 is off. When we apply voltage to our circuit, it turns on voltages for the carry wires and for the output wires, which correspond to our result. And that gives our result 12. If we add another 4 of these full adders, we get a circuit that can add 8 base 2 digits together, our 8-bit adder. Now why 8 bits? Well, it's a convention. Early computers used 1-bit adders, 4-bit adders. Some early systems had as many as 36-bit numbers. There is nothing really all that magical about 8, except that it is the number we've settled on as the proper number of bits in a computer. Let's encapsulate this into its own box because it's easier to keep track of a single box than the 144 transistors that goes into our complete circuit. Pretty cool, huh? A circuit built entirely with transistors that does addition. By the way, one interesting thing about encapsulation is that, in some ways, once we've got our box, we sort of don't care what's in the box, so long as the contents of the box works the way we expect. For example, instead of making our 8-bit adder out of resistors and transistors, we could have made it out of 2 integrated circuits. While transistors may have been one of the greatest inventions of the 1940s, one of the greatest inventions of the 1960s was the integrated circuit, a circuit with multiple transistors in a single little black box. One of these integrated circuits has 4 full adders, all on one tiny little chip. And when we wire 2 of them together, we get exactly the same thing we would get if we made our adder out of discrete transistors. It really doesn't matter what's in the box so long as our box works. And while we've described one way we can build our adder using transistors, there are other ways we can build our little boxes, like using integrated circuits. And that's the power of encapsulation. We can easily change out what's inside so long as what's outside works the same. Now that we have addition, let's worry about subtraction. Subtraction works similarly to addition. We start with the rightmost digit, subtracting the bottom from the top. In this case, 8 minus 5 is 3. If the number is too big, we borrow from the next column from the left. Once we've borrowed from the hundreds column, we can finally do our subtraction. Here, 16 minus 8 is 8. And in the hundreds column, we've borrowed, so we must subtract 1 and 1 from 3, leaving us 1. The same thing happens in base 2. When we subtract 5 from 6, the first base 2 digit 1 is bigger than 0, so we have to borrow. That leaves us 10 minus 1 in base 2 is 1. And in the next column, we have 1 minus 1 equals 0. And finally, we finish our subtraction operation, giving us the final result of 1. Now let's show all possible ways we can subtract a 1-digit base 2 number from another. But rather than build a half subtractor circuit, I'll show you another way we can arrive at building a subtraction circuit. Let's show what happens when we also subtract an additional borrow value. This is what happens when we borrow from this column. We need to subtract an additional one from our result. As always, let's tally this up in a table. And let's rewrite our result in base 2 with the result in D, and if we need to borrow from the next column in B. The second B column is set to 1 if our result is negative. That is, if we had to borrow from the next column in order to finish our subtraction operation. Yes, all those zeros and ones can look pretty intimidating, but if we are patient, we can notice a few patterns. For example, notice this subset of numbers. A funny thing about these numbers, they're our old friend exclusive OR. D is 1 only if X or Y, but not both, are set to 1. So let's add a new column showing the results of X exclusive OR Y. That gets us part of the way there, but notice these numbers are the inverse. That is, we want D to be 1 when the exclusive OR column is 0 and vice versa. The thing is about an exclusive OR circuit is that you can think of it as preserving the first input if the second input is 0, and negating the first input if the second input is 1. Let's apply this idea to our exclusive OR gate's output by adding another exclusive OR gate, this time with the input overflow as one of the gate's inputs. And there you go. We now have the gates necessary to generate the D part of our result. Now getting our output borrow column will take a little more work. Notice something though. Our overflow output is 1 if Y is greater than X, which makes sense. If we're subtracting 1 from 0, we need to borrow. So let's first get not X. And when we AND with Y, notice we get a 1 right where we expected it. And notice that gets us part ways to the final result. But what about these digits? They're not the same. Notice that in each of these cases we have X and Y the same. Now X minus Y is 0, and our overflow is 1, which means we will need to borrow. There are, of course, a couple of ways we can achieve this result. Here's one which has a certain amount of symmetry. First, we get the inverse of the first exclusive OR column. That way we have 1 if X and Y are equal. Remember, exclusive OR is 1 if either X or Y are 1, but not both. That means that exclusive OR output is 1 if X and Y are not equal. But we only want our borrow to be 1 if the original borrow digit is 1. So we'll use the AND circuit. And if we use an OR circuit to combine the results of our two AND circuits, we get the results we're looking for. And in a way this makes sense. The first AND circuit is producing 1 if y is bigger than x. The second is producing 1 if, after subtracting x and y, the original borrow is bigger. In either case, we will need to borrow from the next digit to get our result. Notice a rather pretty symmetry here. We have a NOT circuit feeding an AND circuit. This hints at the idea that we could have also done this as a half subtractor, like our half adder earlier. Let's lay all this out properly, shall we? We have the part of the circuit which subtracts and produces the difference for our digit. We have the two halves of our borrow circuit, and we OR them together to produce our result. This gives our subtraction circuit. Now let's iterate through all the possible combinations of inputs x and y and borrow. There is something mesmerizing about all the flashing lines, but each show the part of the circuit being used to make our subtraction work. And that's our subtraction circuit. This is about as complicated as it gets, so let's encapsulate it in a box. Notice the magic word for all these videos is encapsulation. It's how we get this box and not the confusing nest of the hundreds of transistors that make up the circuit. Again, like the adder, we can put 4 of these together and subtract bigger numbers. In this case, we can subtract 5 from 6. Converting to base 2, we get these values. Remember our convention, a base 2-digit 1 is on, 0 is off. Notice our result and the borrow operations show up on the output wires, giving us the result 1. We can add 4 more, giving us our 8-bit subtractor circuit, which we encapsulate in another box. Now, many 8-bit processors did not have a multiply or divide circuit built in. Instead, they would rely on a computer algorithm to multiply and divide. For example, we're showing how to multiply using a few basic operations. I won't go into this algorithm now, that'll be for a later day. But our multiplication does rely on a few basic operations. One of the most important is shift. Shift slides the bits to the left or to the right. For base 2 math, this is the same as multiplying or dividing by 2. Through shifting and adding, we can multiply. By shifting and subtracting, we can divide. So let's review. We have an adder circuit. We have a subtractor. Our multiplication algorithm requires the use of a bitwise AND. This is where we take 2 base 2 values, A and B, and take the AND of each digit. And it may be convenient to do this with our other circuits for OR, for exclusive OR, and for NOT. There are some very useful things we can do with AND, OR, exclusive OR, and NOT beyond just multiplication and division, but that's beyond the scope of this video. And of course, we need our shift circuits. Notice something about shift. All it does is wires the output bits to the input bits by shifting the wires over one position. There are no transistors here. Right shift is the same, no transistors, just wires. And we will throw in what we call arithmetic right shift. This becomes useful when dealing with negative numbers, but again, that's beyond the scope of this video. For now, we'll need this, so we'll toss it in. All these circuits provide us the basic math operations for our microprocessor. And eventually, these circuits, combined with a bunch of other stuff we haven't gotten to yet, will make up what we call the Arithmetic Logic Unit, the core of any modern computer, the thing that allows us to do math on our computers. In the last video, we showed how transistors can be used to make switches that turn on and off. We also showed how, by putting transistors together in series or in parallel, we could make basic logic gates. In this video, we showed how we can use on to represent 1 and off to represent 0 when counting in base 2. We showed how to build a circuit that can add numbers by using the logic gates from our first video, and we showed how we could do basic addition operations with our circuit. We also did the same thing with subtraction, building a circuit using logic gates from our first video, which can subtract. And we showed how we could do basic subtraction operations with our circuit. We also hinted at other possible circuits we would need to perform things like multiplication and division using an external algorithm. And we showed how these circuits, which can add, subtract, shift, perform basic logic operations on 8-bit numbers, will eventually combine along with other circuits to make the Arithmetic Logic Unit on our computer. Next time, We will talk about how to store numbers in a computer. We'll introduce set-reset flip-flops, show how they can be used to make a D-latch, JK flip-flops, counters, and talk a little bit about why computers have speed limits. Thanks for watching.